Today, we present our work titled SineCompass, an indoor localization system that uses both Wi-Fi and IMU sensors to track pedestrian. This project is the result of Theo Alrich's 3-month internship at the Nara Institute of Science and Technology. In Track 3, we focused on combining data from IMU sensors and Wi-Fi signals to build an indoor localization system. IMU data helps us estimate relative movement, while Wi-Fi signals enable us to globally determine the user's position by analyzing signal strengths from nearby access points. These two methods are combined through sensor fusion. This slide shows the flowchart of our localization method. As shown in this figure, the processing flow follows a general structure. The process starts with accelerometer data and orientation data from the attitude and heading reference system. Accelerometer data is used to compute global acceleration. This is divided into vertical and horizontal components. The vertical component is used to detect steps, while the horizontal component determines the user's direction of movement. These results are combined to estimate step length, allowing us to calculate the user's trajectory. At the same time, the system processes Wi-Fi signals, gathering signal strength data from nearby access points. This data is analyzed with a Wi-Fi fingerprinting technique, which estimates the user's position based on the observed signal patterns. Finally, these two data streams are combined through sensor fusion. By integrating the trajectory calculated from IMU data with the position estimated from Wi-Fi signals, the system provides localization results. The name SineCompass comes from the key method we use for heading estimation. This method involves analyzing the periodic nature of horizontal acceleration. The pattern resembles a sine wave. By extracting the dominant movement direction, we achieve heading estimation. This slide illustrates how we estimate heading direction using the horizontal acceleration components and Fourier decomposition. As shown in this figure, the periodic nature of acceleration during walking is central to this process. To begin, the horizontal acceleration data is transformed into the global coordinate system using orientation information from the sensors. Once transformed, the acceleration signal can be analyzed as a periodic function over each step. This periodic behavior reflects the user's movement pattern during walking. In the figure, the left graph shows the amplitude of the acceleration signal in two directions, the heading direction, labeled as x amplitude, and the orthogonal direction, labeled as y amplitude. The x amplitude generally has higher values because it corresponds to the dominant direction of movement, while the y amplitude is smaller, representing the side-to-side motion. The right graph depicts the offset of the signal in both directions. The offset represents the baseline shift of the acceleration signal and is calculated over multiple steps. While the x direction shows a relatively stable offset aligned with the walking trajectory, the y direction fluctuates more due to side-to-side motion. By applying Fourier decomposition, we extract the dominant frequency in the signal. Step length estimation in our system is based on machine learning. First, we detect individual steps by identifying peaks in the acceleration data. These peaks correspond to the user's vertical motion while walking. Next, we estimate the heading direction for each step using horizontal acceleration data. This gives us the user's movement direction. We then fit the detected step lengths to the ground truth trajectory. By adjusting step lengths to match the actual path, we create a training dataset with features like step duration and acceleration values. Finally, we train a machine learning model using this data. The model predicts step lengths during localization. However, one challenge we faced was the sparsity of ground truth trajectory data. This made it difficult to achieve higher accuracy in some cases. The lack of dense reference points limited the precision of our trajectory fitting. RSSI fingerprinting is implemented using AutoML with a framework called AutoGluon. This approach allows us to efficiently train models for location prediction tasks. These tasks include floor levels and geographical coordinates. For floor prediction, we treated the task as a multi-class classification problem. The model predicts the most likely floor based on RSSI features. For latitude and longitude, we used quantile regression. This technique not only predicts the most likely values but also provides confidence intervals. As a result, it enhances the reliability of the predictions. We developed SineCompass as a system for accurate localization. It combines IMU-based PDR with Wi-Fi fingerprinting. The system has three key components. First, heading estimation. This uses Fourier decomposition to identify the dominant direction of movement. Second, step length estimation. It detects individual steps, determines movement directions, and learns step lengths using ground truth trajectories. Third, RSSI fingerprinting. It predicts floor levels using classification and latitude/longitude through quantile regression. Thank you for listening.